All right, well, good morning, everyone. Thank you for joining Flex Train, a training opportunity brought to you by Johnstone Supply. So as we continue talking about heat pumps and electric furnaces and dual fuel systems, one of the things that we wanted to spend a little bit of time today talking about is general electric furnace service basics. So I know when I was out in the field, electric furnaces, when you walk up to them, they're a lot simpler as far as components of a gas furnace, but it's not something that you would walk up to an electric furnace and go, okay, there's half as many things here, so I'll have half as much time on this job. Not so. There are a lot of things to go over in an electric furnace that gets overlooked. And I want to cover a few of those things today so we can just look at the fundamentals of electric furnaces and the components that we are there to investigate. You know, as our job as technicians, we're there to make sure that this system is tuned up and running properly. So we're not just looking at the components themselves as much as we're looking at an entire operating system. You know, this is the primary or secondary heating source in a system. If it's a heat pump, it's our secondary, but I have seen electric furnaces that are standalone furnaces, you know, matched to an air conditioner. So it could be the primary heat source. And I couldn't tell you how many times I've gotten out into the field and found electric furnaces that were running, but limping along and not properly diagnosed, you know, had failed components. So we'll look at all those today, and we'll look at how to check some of those. Starting with static pressure. You know, we always go back to understanding the effect of static pressure on the total HVAC system. And with an air handler, we have to remember how the manufacturer is setting those airflow standards for that piece of equipment, because it is different. You know, in our static pressure class, we talk about how there's all these different combinations of equipment, and those numbers, those static pressure charts that tells you how much airflow that blower is capable of, comes from the manufacturer based on that package. If it is a gas furnace, it is only for the gas furnace. It does not include the evaporator coil because they don't know what coil that furnace is going to be matched to in the field. So they set those ratings based on the blower for that furnace. With a electric furnace, it's a little bit different scenario because it has the coil already assembled as part of the component, the complete unit, right? So they've already factored in the amount of static drop that is happening across that A coil. So the chart, if I took a half horse blower motor with a 10 by 10 wheel, so an exact blower, and I put it in a furnace, I would have a different airflow chart for that blower in that furnace than if I pulled that blower assembly out and I put it into an electric furnace, because that electric furnace is already adding in that static drop across that coil. So I have a different reference point. So with a air handler, I am only including the things that came from the factory on that. So I haven't seen them in a long time, but I have seen air handlers that came with a hog hair filter installed in them. It's been a long time, shows a little bit of my age, but we used to have those. You know, hog hair was a pretty common filter that came from the OEM in the piece of equipment. So if I had an air handler that has a factory installed filter in that, that filter is also included in that pressure versus CFM chart for that blower. Most of the air handlers that you get today do not include a filter. They may have a slot, a 1-inch slot in the actual compartment, but that is for you to field install an air filter. So the air filter is not included in that calculation. So we look at our static pressure on our total system measured between the return and the coil and between the blower and the supply plenum. If we install a 1-inch filter in that cabinet, we cannot rely on that reading. We would actually have to put a secondary port in that air handler to be able to read the true pressure from the coil through the blower, not including that filter. So that's a big misconception in the field. So if someone gives me some data, so maybe if I'm doing a tech support call and we're working on an air handler and I ask them to check the static pressure on that, and they check it at the return right in front of the air handler, and they check it at the supply right past the blower, which is where they would typically check that, but they have a filter in that air handler, it does not include the pressure drop across that filter. I actually had one last summer that I went and did a tech support site visit on. And the readings that I was getting from the technician didn't jive. You know, he was the pressure readings that he had on the return and on the supply were in the 0.6 to 0.7 range. But yet he was having blower fault codes. That ECM blower motor was tripping out on an internal overload. Yeah, total static. I don't remember exactly. I just remember it was between, it was a little high, but not enough to kick out that ECM temperature overload. Because remember, a lot of our temperature overloads are around 0.8 to 0.9.
Yeah.
That internal overload starts warming up. So what he was telling me shouldn't have been tripping that overload. And I was like, man, are you sure? Have you checked the filter on that thing? Yeah, we've got a 4-inch media filter in front of it, and I'm checking between the media filter and the air handler. I'm like, man, you've got something going on. Have you checked the coil? Oh yeah, I'm sure we've checked the coil. And they wanted a new outdoor unit, right? I was like, well, it doesn't happen that easily. Let me come out here and let's take a look at this thing and let's verify exactly what's going on in this system. So I went ahead and did a site visit with him, had him get his manometers out, put his manometers on the return on the supply. And I'm like, yeah, those numbers are a little bit off. And then we checked it to atmospheric pressure, and the numbers weren't jiving quite still. And so I thought, well, let's verify what we have on this blower motor. Start pulling some panels off from this thing. Pull the cover off from it. Let's take a look and see what we have. And as soon as we started taking the covers off the front of the filter, we found the plugged 1-inch filter that the installers put in the system when it was originally installed. So it had a 1-inch filter that was plugged solid, and it had that 4-inch media filter, but the static pressure wasn't showing up because the static pressure was behind the 1-inch filter. Yeah. So if you have a 1-inch filter in that cabinet, you're not getting the correct static pressure for that blower motor. So what was happening is that 1-inch filter was plugged solid, and we had a 1.2-inch total static pressure when we included the static pressure drop across the filter, which is more than sufficient to cause that module on the back of that ECM motor to overtemp and throw a B3 fault code for over temperature power limiting. So understanding the placement of that filter in an air handler is critical. So if we have a 1-inch filter in that air handler and it did not come with the filter from the factory, we're not reading proper static across that thing. So be aware of proper static pressure readings because it throws those motors off drastically. This particular chart is it's a little over a year old. So this is when we were using a permanent split capacitor blower motor. We've now shifted over with this ARUF to a ECM constant torque. So most everyone in the industry has shifted from permanent split capacitor motors over to some type of an ECM because of our federal energy requirements on our motors, right? There's a few PSC out there that are still hitting that requirement, but it's just barely, and it's a very, very small amount of them. So most of them went over to ECMs, but with the PSC, we can see that our airflow just nosedives once we get up into that 0.6 and above range. So knowing what that static pressure is will truly affect the airflow, right? Because airflow is going to be critical even on our electric furnace to understand the overall operating condition of particularly our electric elements. So if we look at an element, an electric element, it's a very simple construction, right? It's a high resistance wire that is insulated inside of ceramic insulators. So it's basically an open wire, right, that we're going to apply voltage to. And because of the resistance in that wire, it's going to start converting some wattage, electrical wattage, into heat energy, and typically does it 100% efficient. So for each watt of electricity we're bringing in, we're producing a watt of heat out. But if we think about what that wire is, it's a material that's designed to run in a certain temperature range. And like all materials, particularly all metals, at some temperature, those things are going to break down, right? So we try to maintain a fairly specific temperature on our elements. And once we get above that temperature, we're going to start degrading the actual element itself, and we're also going to overheat those ceramic insulators. So it's fairly common to pull a heat kit out and find deterioration on the elements and to find ceramic insulators that have gotten so hot that they have broken in half. And that's what we're there to do. We're there to evaluate this system. And the best way to do that is to understand what the elements are actually doing. How much heat are they producing and how much air are we moving across those things to make sure we are getting sufficient air. So we can calculate that fairly easily, actually. If Greg Millsaps was on here, I probably wouldn't be able to talk right now. He would be running with this show because he's so passionate about understanding airflow in electric furnaces, because we overlook that so many times. If we were working on a gas furnace and we're doing a tune-up on it, we're going to check temperature rise, right? We don't always do that with an electric furnace. We assume that some of our variables are constant, and they're not. We have things that change, and so we need to understand what those changes are. So if we look at an electric heat strip, we can simply take our meter, measure the amps that are being drawn by that heater, and then take our leads, put our meter on voltage, AC, and we can check the voltage that is being applied to that heater. Now we can get the exact watts. So like last week when we were talking about using Ohm's law and taking a piece of our pie chart to take two, if we have two known factors, we're going to have our third, we're going to find it, right? It's just a mathematical calculation. Well, when we're talking about watts, we are simply multiplying our measured amp draw for that element times the voltage that's being applied across it, and that gives us our watts. That's how much heat energy is being produced from our electric energy. That's what we're measuring. Now, if we want to convert that over to BTUs, it's as simple as using a constant of 3.412. So if I take my watts times 3.412, that is my actual BTUs of my heater based on my voltage and my amperage. And that changes. That depends on my voltage, because if I have low voltage, remember, if one number changes, I'm going to go the other direction on one of my other numbers, right? So I can use that to calculate what my actual BTU rating is of that particular element. And I want to do that, and I want to write that down. I want to track the watts of my electric element to see if it is degrading, to see if it is changing its resistance over time. So if I take my watts times 3.412, that is my actual BTUs that's being generated by this furnace. If I was doing a heat load calculation on a house, this is exactly what I would do to size my elements. As I look at my BTUs that's being produced by it. We always think of BTUs on a gas furnace. We never think about BTUs on an electric furnace, right? Well, it's pretty simple. That's our watts times 3.412, and that is BTUs. Now we've got something really cool to work with. If we take our BTUs, so let's assume I have a 15 kW heater. That 15 kW heater, I actually calculated, and it wasn't producing 15 kW. Whoa. Why isn't it producing 15 kW? Well, it depends on the voltage that's being applied to our heater. If we say that a heater is 15 kW, that's a broad reference. That is just saying it's in this ballpark. That is not exact. So we calculate it, we get the actual wattage, right? And so now we do our wattage times 3.412, and we have our BTUs. So if I take this 15 kW heater, and I am now getting calculated 48,999 BTUs, which that's about right. 15 kW is approximately 50,000 BTUs. 30 kW is approximately 100,000 BTUs. So if I calculated exact, I would have came out with 48,999 BTUs off from this unit that is 243 volts, and that's what we're pulling off from it, right? Well, now all I got to do is check my temperature rise. Check the temperature from my return to my supply. That difference, that delta T, is my temperature rise, just like I was checking temperature rise on a gas furnace. If I simply use that 1.08, which we're going to say is a constant, but it is not, I'm going to explain that one here in a minute. We're going to use that as a standard number. Let's just say that. 1.08 times that temperature rise. So say this particular one, I had a 70-degree return and I had a 110-degree supply. I had a 40-degree temperature rise. So I just go 1.08 times that 40-degree temperature rise is 43.2. And so if I took my total BTUs that I had calculated, 48,999 divided by that 43.2, voila. I have the exact CFM that my blower is running. I don't have to put a vane tool on that to measure how much airflow is coming through my duct system. I've actually calculated what my CFM is on that thing. If I didn't have me a manometer and I had an actual static pressure versus CFM chart on my piece of equipment, I now know what my static pressure is on my system without putting probes on a thing. Simply using my meter and some temperature probes, I can calculate what my actual CFM. Yeah, so the question was this include the compressor? Is this heat strips only? No, this is only our heat on our electric furnace. So this is while our electric furnace itself is running. So if this was a heat pump system with an electric furnace, we're going to have this in emergency heat so that we're not including the BTUs of our compressor, because that would actually throw all of our numbers off. So we're only doing this with our heat strip. But yeah, it's a good point. Make sure that thing is in emergency heat when we're doing this and the compressor's not running. Because remember, the compressor is also moving BTUs, right? So we're just going to be looking at the efficiency of our electric heat strips right now. And we're doing this to make sure that we have a proper temperature rise on our electric furnace, because electric furnaces do rely on a temperature rise. It's not on the nameplate like it is on a gas furnace, but we do rely on a temperature rise on that. And we can modify our airflow a little bit to control that temperature rise to make sure that it is comfortable for that homeowner, especially if they've had a gas furnace in the past and now they went to a high efficiency heat pump with an electric furnace. If we don't have that temperature rise set comfortably for them, they might not like their new system, simply because the air that's being blown across them, right? Some of our equipment limits what we can even set that temperature rise to. If I look at like the Daikin 1+ thermostat on an inverter system, it will not allow me to decrease my airflow for the electric heaters. It says, hey, I want a round 30 to 35 degree temperature rise, and I'll do the adjustments to make sure that that happens. And so it's preset. So we can increase it a little bit, which is going to run down our temperature rise, but we cannot raise the temperature on that electric furnace because it's trying to maintain the integrity of the heating elements. It wants those heating elements to run a long time, hopefully a lifetime. And we know that when our temperature rise gets high, especially when our temperature rise gets above 50 degrees, we're going to start burning up elements on an electric furnace. So the rule of thumb on a high efficiency furnace is 35 to 55 degrees, in that ballpark, right? So I can safely say that most manufacturers are going to be in that range on a gas furnace. I have seen some go higher, but not typically. We want our heat exchangers to last, right? So we put that temperature rise of 35 to 55 degrees or so. An electric furnace is actually similar in that temperature rise. We typically are going to be 30 to 40 degrees temperature rise on an electric furnace. So when we're checking a electric furnace, we want to make sure that we check that temperature rise. We want to know what the actual temperature is on that. We could also calculate that again if we really wanted to. We could go back to using our meter and verifying all of our kW and our BTUs. And if we know the power factor, the actual voltage going through our motor, we can calculate that out. So we could even set our CFM based on our temperature rise, not by temperature probes, but by watts, BTUs. So that's when we get into this other calculation. So if we simply wanted to do that, we've already figured out our CFMs. We can now do our kW times 3412, which is getting BTUs, times our voltage correction, times that 1.8 factor, divided by our CFM, and voila, we have a calculated temperature rise for our piece of equipment. So if we look at this chart, this heat kit nominal chart, that is giving us approximately those numbers. And it's a pretty good chart to have. Most electric furnaces have some type of a chart in it. And I've noticed a lot of the Goodman and Amana and some of the Daikin's actually have charts for a variety of voltages as well. So they'll have one based at 230, one based at 240, one based at 208. And that gives us a opportunity to see what those correction factors are based on the voltage. So if I look at this particular one and I had approximately 230 volts AC, and I measured, like say I have a, let me grab my Sharpie here. If I had a 15 kW heater installed in this electric furnace, and I set all of my dip switches up to run 1200 CFM, I could actually measure the performance of my blower simply by checking my temperature rise. My temperature rise should be 32 degrees on this thing. So if I go check my temperature rise and I find that I am running a 44 degree temperature rise on this system, but I had my blower set at 1200, now I need to go find out why. Why is my blower not moving the correct amount of airflow? Typically, it's going to be like a dirty blower wheel, something that is impeding our airflow, or high static pressure, dirty filter, right? So looking at that chart, we can get a general idea of the operating of our duct system and the operating of our total HVAC system based on temperature rise and CFM and KW. So really good charts to be able to understand what's going on inside of there. The reason that I say that 1.8 is not a constant, you'll see this in many descriptions. They'll say that 1.08 is a constant. I will tell you that we use that as a common number, but it is not a constant at all. Here's where that is derived from. It is derived from the standard of air, which is what we consider the air that is in our breathable atmosphere at 70 degrees Fahrenheit at sea level with 50% relative humidity. It has a weight to it, right? If I take a cubic foot, 1 foot by 1 foot by 1 foot deep of air, if I was able to take a knife, go into the air and carve me out a 1 foot cube, it actually has weight to it, right? It has that 50% humidity in it. It has water droplets in it. It has all these different gases that are suspended in it. If I was able to put that 1 cubic foot of air on a scale, it would weigh 0.07 pounds. That was its weight, right? Well, what if I take that 1 cubic foot of air at the top of Mount Everest? Doesn't weigh the same, does it? It's got different gases. It definitely has different humidity. It's probably going to have almost none. It's got a different pressure on it, right? So we use that number, 70 degrees Fahrenheit at sea level with a 50% humidity, to say that this is a reference point and it has a weight. It also has a specific heat of about 0.24 BTUs per pound, right? And we know that there's 60 minutes in an hour. So if I'm going to look at the rate of that, I'm going to now be calculating a BTU per hour, because we tend to use that number quite often in our industry, don't we? BTUs per hour. So that's actually what we're doing, is we are coming up with a correction factor for BTUs per hour. So if we take that 0.75 pounds per cubic foot, we multiply that times 0.24 BTUs per pound times 60 minutes, so we can get it up to an hour. That now gives us a correction factor of 1.08. So if any of those numbers change, if our temperature is different, if our humidity is different, if our pressure is different, it changes all of that calculation. So if we were using this in a controlled environment, say we were working in a electronics lab that had a air handler that was remote to that room, and in that electronics lab, it was an oxygen-free lab that was nitrogen filled. Our weight of that air is going to be very different, and then we would have to recalculate it. But that's all we do. We just recalculate what the actual weight would be, what its heat transfer would be, the BTUs per pound, and now we can come up with a different number. But for standard measurements, the reason we call it standard air is because it is a reference point for most of the air that we work with. It is a average. So whenever you see that 1.08 and someone says that it is a constant, well, it's somewhat of a constant for our industry, but it is variable, right? So it's important to know how we're moving our air. If I were to use that previous calculation for my temperature rise, and say I did a temperature rise, and I know that, say I've got a an ECM blower motor that should keep a constant airflow, right? And I set my dip switches to run 1200 CFM. And I should be running about a 35-degree temperature rise, but I put my temperature probes on my return to my supply, and I go, wow, I've got a 45-degree temperature rise on the system. For some reason, I am not moving the 1200 CFM that this blower is supposed to be moving. If it's a constant torque, it's trying to maintain a certain torque, a certain load on that motor, and it's going to draw more amps trying to do that. So if I measure the amps on my motor and I go, man, my motor is working really hard to try to move this 1200 CFM, and I just took a temperature rise and it's saying that I'm actually probably only moving 1000 CFM, I need to go figure out why my air is not moving, right? That's when I can get into looking at my coil and looking at my blower wheel to see what type of airflow I have in my system. So those numbers, those temperature rise and verifying the CFM is going to tell us what our motor is actually doing. And the number one culprit of motor failures is failed airflow, because we didn't do our job, right? That motor is trying to get that air to move, but if it has a packed up fan wheel, which has a cup to it, it can't move the air. If it has a dirty coil, it can't move the air. So we have to be able to check these things, and it's overlooked, pretty common in our industry. When we get into our heat kits, we can actually check the resistance of those things. So if we take a heat kit, we can use our same Ohm's law to figure out how many ohms is going to be going across that heater. So if I had this particular heater and it was a 5 kW heater, and I knew that I have 240 volts for that sucker, I could actually disconnect one lead. I typically do one. You can do both of them if you feel more safe about it, but you can disconnect that one lead so we can isolate our element, put our meter on ohms, horseshoe setting, remember? Get that, don't believe me, we get that call once in a while. It's a horseshoe setting. So we put it on ohms so that we can read the resistance across it, and it's going to be in that ballpark, 11.5 or so. So by checking ohms, we can check the integrity of our element without even having applied voltage on it. One thing that we run into a lot is poor connections, which generates heat. So anytime that we change the resistance of a connection, when we turn a conductor into a resistor, we're going to generate heat. And because we have so much current passing through our components, they're going to be the ones that are most likely to generate that heat. So anytime we see a heat source from a conductor, that part needs to be replaced. And we're going to see it a lot in our temperature limits and in our overloads and in our crimp connections. So even the terminals that we use on our wires have a specific temperature range. And I'll tell you, the one thing that I find in the industry is that our crimp terminals, our wire terminal ends, don't have the same temperature ratings. And it's important that we know what those ratings are, because if I have a wire, that most of the ones that we use are 90 degrees C. If I go to the auto parts store and I get some end connectors, they may not be 90 degrees C rating. They're probably going to be 60 degrees C ratings. So if I take off a 90 degrees C terminal because it was loose and it was starting to arc, and I thought it was a good time to change that, and I cut it off and I restrip it down to clean wire, and I crimp on a 60 degrees C connection and put back on that, you're going to find that terminal burning up. So we have to make sure that we're using connectors that have the same temperature rating as the insulation that is on our wires. And you'll see, if you read on that wire and the wire says that it is a 90 degrees C wire, we need to use a 90 degrees C terminal on the end of that thing for repairs. Another common culprit in our heat kits are failed heat sequencers. A heat sequencer is literally just a heating element that is slowly warming up until it can put heat onto a bimetal strip that will pop and make contact for us. So every bimetal strip starts out 100% on day one, right? It's tested for its integrity. That is the last time that bimetal strip had 100% integrity. From the very first time that it gets used, it is continually wearing down. The metals are continually degrading. We are constantly making an arc between our contacts and generating heat and generating burnt metal deposits. So a heat sequencer is something that needs to be checked, and it needs to be replaced often. When you start seeing the scorch marks coming out of the ends of our heat sequencer, when we start seeing dust building up around the contact points of our heat sequencer, it's time to replace those things, because that heat sequencer is the only thing that is going to time on that heater. If our timing starts wearing out, our heater is not going to come on. So I've had a lot of furnaces in the past that had heat sequencers that would stick, or heat sequencers that would not make, and therefore we don't have a functioning heat kit. So that was a common replacement part for me, and it should be a van stock. You should have a universal stack of sequencers on your van as a replacement component for electric furnaces. Auxiliary limits, those are, we're going to have two different styles of limits on an electric furnace. We're going to have a automatic reset, and then we're going to have a manual blow. That manual blow is just like a fuse. When it pops, it's a one-time blow because it got really hot. Our auxiliaries are around 100, typically around 150 degrees for most of our brand. It can go up to around 190 for these automatic ones, but most of the time they're going to be around 150, and then they're going to reset back around 100 degrees. But the same thing with those. Those are also a bimetal style limit. Those are there as a emergency source, right? Hits 150 degrees, which means the temperature rise has gotten too hot. It's there to open up so that it can protect that heating element and those ceramic insulators. Gets down to 100 degrees and cools down to 100 degrees, it's going to reset. But if we have a plugged filter on this electric furnace and that heating element is constantly 150 degrees, let's open. Okay, let's let the blower run till we get down to 100 degrees. 100 degrees. Okay, let's close. We're ready to go again. And off we go. We warm up, get to 150 degrees. And oh, I've got to open up and I got to cool back down again. That was supposed to be a safety switch. Now it has become a regulating device. So when we have that complaint, hey, my electric furnace is, the blower's running all the time, the heat is cycling on and off, on and off, on and off every 5-10 minutes. Well, that is telling us that our auxiliary limit has been opening and closing, and it's not supposed to. It's supposed to be there as a safety device. So if we have one that has been opening and closing routinely, I recommend replacing it as a service part. They're very inexpensive, and they were there to be a safety device, not an operating device. They were never designed to be a functioning part of that system, not a regulating part. They're supposed to be there as an emergency function. So if we have a dirty filter, a plugged coil, plugged blower wheel that's been causing that limit to reset regularly, it's time to change that thing and put a new one in. And that is our link. That is our thermal fuse, and that one is typically between 300 and 400 degrees. When it opens, it's just a fuse. That thing opens, it's time, you're going to have to replace it because it's shot. But if it's gotten that hot, that means that we've had poor airflow, that it's been cycling back and forth on our auxiliary limit until there was finally enough heat in that compartment that it popped my fuse. So if it gets that hot, it's typically because it had a blower motor that failed or a coil plugged solid, something of that nature. When we get into wiring, it's really important to understand the difference between O and B on an operating system. For all of our heat pumps, most of our heat pumps, we're going to be operating with the same principle. We're going to be using Y to bring on our compressor. We're going to be using W to bring on our auxiliary heat or our electric heat. And then we're going to be reversing our reversing valve with O/B. And not everyone understands the difference between those. So in our history of heat pumps, we have had two different philosophies of the manufacturing of our outdoor unit. One has decided that if I have a failure of my solenoid, if I have a failure of some wiring going to my reversing valve, I would like for the steady state or the natural state of my outdoor unit to be in heating mode if I have a failure. The other part of our industry has decided, well, we would rather the safe mode be cooling for our outdoor unit. I still don't understand that philosophy. I could go without cooling, but I'm not going to do very well without heating, right? So I would say that 80% or more of our industry uses O. So what O is doing is O is energizing our solenoid, our reversing for cooling. So the natural state of most heat pumps is actually heating. And then we energize O for cooling. There are manufacturers out there, particularly Ream-Rude. They have stayed with the B philosophy, and as far as I'm aware, are still using the B philosophy. So that, and I don't know of anyone else that's using that. Do you, Paul?
Just there are other brands
that
are labeled, yeah.
Yeah, the sub brands.
So I actually kind of tend towards that way personally.
Do you?
Yeah, because I feel like, and this maybe is the consumer in me, but if it breaks, usually people with heat pumps have an alternate source of heat. So that's if it breaks, I still have a heat source and a cooling source. Whereas if it's the other way and it breaks, you're stuck with heat only.
And I've never thought about that. And that is, you're right. I have never looked at it from that perspective. It would still leave you with a heating source and a cooling source.
Right.
Whereas if I have a solenoid that fails on a O system, I have two heating sources and no cooling source.
So from a consumer perspective, I feel like if it breaks, hey, at least I'll have an air conditioner. Buys me some time.
That's a great point.
I don't know.
That's why I love having you around. And that's the great part about doing this type of a program, is that it's not all one person perspective. Is we get different perspectives, because I have never thought about it like that. But you're right. That would give you a heating source and a cooling source. So Ream-Rude is still using this philosophy.
Yeah.
And what they are doing is their natural state is cooling. And then when it is in heating mode, they're going to energize that reversing valve. So it's the same wire. OB is the same wire. It is our reversing valve wire. It's just done differently depending on the manufacturer of equipment. So if you are taking a thermostat off and you're on a heat pump system and you're replacing it with an aftermarket thermostat, they all will have that distinction of O/B. And we have to tell it what we want that terminal to be. Do we want to energize it in heating for B, or do we want to energize it in cooling for O? So I've had tech support calls where guys have had, hey, I just put a new thermostat on this wall and the sucker is running in heat when it's supposed to be cooling, and it's running in cooling when it's supposed to be heat. And I go, well, do you have a Ream-Rude? Yeah, I sure do. I was like, well, now you have B, you don't have O. And they go, what's the difference between B and O? And I said, well, one is a normally open set of contacts, one's a normally closed set of contacts. That's it. So all we're doing is deciding how to energize our reversing valve based on our outdoor unit. So you'll see that, and gets very misunderstood. I've had guys come back and follow other contractors that have replaced thermostats and couldn't figure out what the deal was. And then all you do is go into your menu, your setup menu, and you change that from an O to a B, and now it is switched, you're reversing. And it's always good to make sure that we're checking our condensate traps as a routine, as we're there checking out our electric furnace. It's good to see what's going on inside of our traps as well, and to make sure that we're using the proper type of trap, because we're now pulling against our blower.
Can I make a comment on that quick?
Oh, yeah.
As it says there, you know, anything on a negative side of a blower needs to be trapped. Those measurements, those are actually more important than people think. So people think as long as it's got the little P trap U in it, no big deal. We can put it in a running trap. Well, as we start moving, or have moved, into ECM motors, they're going to ramp up if something happens. And if you get too strong of a negative pressure because the blower motor is running hard, you'll actually suck that thing dry.
And overcome
So
it.
you do need to have a 2-inch minimum or a 3-inch minimum. Overall, usually it's a 5 to 6 overall that manufacturers want total.
That's right.
That is important. So
yeah, because those running traps will not, because you got to think about it, it's all about pressure, right? When we talk about water column, what is water column? If we go way before, if you go back and watch our manometer class and our pressure class, you'll find out that we originally had a 1-inch cylinder of glass that we put water in. And when we hooked a hose from it over to our ductwork, the negative pressure would pull our water up that glass. On the other side, it was doing the opposite, right? So our trap is still that water column. So if I have a 1/2 inch of negative pressure on my blower, that means I can move that water inside of that pipe at least a 1/2 inch up from its standard state. If that is an inline style trap, there's not enough room there. That trap is just a little bucket, maybe an inch deep, to hold water in. It's only able to be used on the positive pressure side of a system. So on that negative side, we have to have that clearance so that when we have a restriction on our return side, when our blower is pulling hard, trying to keep its airflow moving, our water is actually inclining up that stand, that minimum 2-inch stand. And if we have very high static, we're going to pull all that water right back into our unit. And I've had that. I've had guys do installations, go, man, I am pulling water out of my trap and it's getting all over my coil. It's getting all over my cabinet. And I go, what? You got high static pressure. And I go, oh, really? I was like, yes. You got more than 1/2 inch and it's pulling it right out of your trap. So verify your pressures and verify that you have the proper trap on it. Great point. So
I've actually, complete side note, I've actually seen a plugged heat exchanger or starting to go plugged, and the inducer motor produced enough negative pressure that it sucked the condensate trap dry
out of the trap.
So
I'm actually been having kind of an issue with that. When on our condensing furnaces, we have, it's called a front cover pressure switch. And a lot of manufacturers are using a front cover pressure switch. When you read the installation manual of that, you're required to put a vent on your standpipe for your furnace. What I am finding, for your condensate line. What I'm finding is that companies that don't do that, or companies that put caps on top of that, I get enough back pressure that I suck all of that water out and I lose my pressure on my front cover pressure switch. So it's important to see what these installation manuals are. Don't rely on what you have done in the past. Rely on what's on between page 5 and 9 of our installation manual on proper condensate traps on installations. So very important. And just a handy little troubleshoot on electric furnaces. So blower turns on and off, then we've got some kind of cycling. Well, then we need to get in and take a look at our limits. We need to verify our motor overload, because so many of our new ECM motors will shut themselves down. So a ECM motor, typically in that 0.8 to 0.9 inches of static, is going to protect itself and reduce, if it's a variable speed, a true variable speed ECM, if it hits that temperature limit in its module on the back of the motor, it will reduce itself down to 35% and it will stay there. So if we have a blower motor that's 100% and then 35%, 5 minutes later, after it cools down, it's back up to 100% and then going back down to 35%, you've got a high static issue, and you're probably gotten a high blower fault code on your control board or your thermostat on a communicating system. So blower runs, but not enough heat. Well, goes back to verifying what our airflow is and to make sure that we're sequencing our heaters in properly, making sure that we're not over temping our elements and making them shut down on auxiliary heat. And no power or voltage, man, I've seen so many times that those heat sequencers have failed, and that is just a switch. That's just a contact. So if our heat sequencer is failing, it will not bring on our heating elements, or it'll have a voltage drop across it, which reduces our voltage, which now is going to reduce our total wattage. And motor not operating, but there's a proper voltage at the motor. Well, then we got to get into our controls, capacitors, and modules. It's on the back of those ECM motors. So just a little bit of info on troubleshooting an electric furnace. Anybody have anything that they would like to add, comment, join in on the conversation for? Okay, well, I guess we'll wrap it up. Appreciate everybody joining us. And as our snow is getting to be removed, I'll get back together on doing a rebuild of a electric furnace heat kit. Everyone have a great day, and we will see you next time.